I want to do some examples taking a look at pressure and how it relates to some properties of Earth's surface. So the first thing I want to look at is the very deepest part on Earth's surface, the bottom of the Marianas Trench, also called Challenger Deep. And if you take a look at the depth, the maximum depth is around 10,900 meters. And physics textbooks tell us to use an approximate density of salt water of 1,020 kilograms per cubic meter. So from the pressure formula, the pressure at the bottom is going to be the pressure on the surface of a fluid plus the density of our fluid times the strength of gravity times our depth in that fluid. So atmospheric pressure at sea level, the surface of water, is about 100 to 1,000 pascals. The density of seawater, I said, is 1,020 kilograms per cubic meter. The strength of Earth's gravitational field is about 9.8 meters per second squared. Over the course of about 11,000 meters, that will vary a little bit, but we're going to assume it's constant. And our depth, which was first reported in the 1800s and has been confirmed many times, is 10,900 meters. So if we multiply all of this out and then add 101,000 pascals, that gives us 1.09 times 10 to the 8 pascals. And since a bar is 10 to the 5th pascals, that would give us 1,090 bar, which is about 1,080 atmospheres, since an atmosphere is just a little bit greater than a bar. So, we'll check ourselves in just a minute against what we've actually measured down there. How high is the top of the atmosphere, then? Well, if you think about it, air is a fluid. So as we go deeper in air, pressure would increase. As we go higher in air, pressure would decrease. And that's how your little personal fitness tracker is able to tell whether or not you've gone up steps. It looks for a pressure difference. So if the pressure drops while you walk forward by just the right amount, it can tell how much altitude you've changed. And if you're out for a walk and the pressure drops really rapidly, you know, your little personal fitness tracker might tell you you just ran up or down the top of a skyscraper, which has happened to me at least once. So, for air, at standard temperature and pressure, its density is about 1.21 kilograms per cubic meter. So, same atmospheric pressure relationship, only here we're looking at the pressure at sea level. And the pressure at the surface, well, if we run out of atmosphere, where are we? We're in space. Space is just a vacuum, no pressure. So, we'd have, in theory, the density of air times the strength of gravity times the height of the atmosphere, giving us atmospheric pressure. So if we use that to estimate the height of the atmosphere, that height would be 101,325 pascals, adding in that little bit extra to try and help boost our measurement here. Density is about 1.21 kilograms per cubic meter, and the strength of gravity is about 9.8 meters per second squared. Now again, as we go up, that is going to drop, but we're going to assume that the effect is pretty small, and if I calculate out that result, I get a height of the atmosphere for 8,600 meters. We'll come back to that. Let's check ourselves first with actual experimental measurements from Challenger Deep. 1,086 bar, which is pretty much what we expect to see based off the numbers. And the reason for that is water is largely an incompressible fluid, which means as you increase pressure, the volume of water stays almost constant. Now, this should sound like a very unreasonable number if you think about how high planes fly. 8,600 meters is about 5.3 miles. A transatlantic flight can fly higher than 8 miles in the air. Planes don't fly through space. So clearly that seems pretty small. And in fact, the legal definition of space is around 100,000 meters, 100 kilometers above the surface, which is roughly 60 miles. And that's roughly the point where air resistance becomes so small that it really isn't a factor. And the reason for this huge difference, 100,000 isn't 8,600. 100,000 is because density drops off as pressure drops off. Gases are compressible. So as we start going higher and higher in elevation, the pressure starts dropping, which means the change in pressure gets smaller the higher we go. So there's this feedback built in. So instead of linearly decreasing to zero, which is what this model expects, we're gradually tapering off. And even at 100 kilometers, there still is a little bit of atmosphere, just not a whole lot. And at about 10,000 meters, which is the top of Mount Everest, there isn't much atmosphere at all, which is why climbers that go to the summit of Everest tend to bring air with them. Thanks for watching.